Lesson 3.3 for PreCalc is going to discuss all the properties of logarithms, and this is actually one of my favorite lessons, so I'm really excited for this one. A little bit of review from Algebra 2. We're just going to take them to a more extreme level here in PreCalc, so you're going to see a lot of the same properties. So remember, exponentials and logarithms are just inverses of each other, so it makes sense that their properties are kind of related to each other as well. So there's the product property for exponents, and then the quotient property, and also the power property. And we're going to see those similar properties popping up here in logarithms. So I'm not a big fan with like their lack of use of parentheses here. So inside of a logarithm of any base, you would have a multiplication problem. Well, that's going to split into an addition problem of the log of the first plus log of the second. So similarly, if you have a log of a quotient problem, that would split into the subtraction of the two logarithms, and it has to be in the correct order where it's log of the numerator minus log of the denominator. And then the power property states that, and this is actually the whole point of a logarithm, if there's an exponent within the logarithm, that exponent can be relocated down in front of the logarithm. In my Algebra 2 class, we call that the Mario property, because we think about like in like the old school Mario game when he like jumps up and punches the brick and then the things slide out. So anywho, if you can visualize that, that's great. If you are an Algebra 2 student of mine from before, you probably remember us talking about the Mario property. So same properties here in your notes, same properties that you had in Algebra 2 notes as well. So our first example, and these are old ones, but I like to throw these on the smart file here because you're going to have a no calculator test coming up real soon. So remember, our log properties say that if you have a log of base whatever, and then inside that logarithm is another base raised to some power, log base b of b are going to cancel out, and then the x is just your solution to whatever that problem is. So for this question, if I could rewrite this problem as a log base 6 with a 6 inside of it, you'd be good to go. So first thing I'm going to do is I'm going to change the third root to a 1/3 power, and then instead of 36, I'm going to call that 6 squared. Well, if I use a little bit of exponent rule here, I could combine these exponents together and make a 2/3 power. So log base 6 of 6 to the 2/3 power, log base 6 of 6 will cancel, leaving you with just 2/3. So again, no calculator test coming up, so we got to be ready for these. Remember, the natural log has a base e, so natural log and e will cancel. This is just a 9. And then plus 4 times, again, natural log and e will cancel. This is just a 3. So 9 plus 12, which is 21. Okay, evaluating this logarithm. Well, a couple of different things we could do. We can evaluate them as they exist, or we could condense them back together into one logarithm and then evaluate it. And it's totally up to you. We can even do this problem multiple ways if you'd like. So if I rewrote 8 as 2 to the 3rd power, forget this 8 business, log base 2 of 2 cancels, and this is just going to be a 3 drop down. So it's 3 times 3 plus 5 times, again, rewriting a 4 as a 2, it'd be 2 squared. So log base 2 and 2 cancel, and the 2 drops down. So you end up with 9 plus 10, which is 19. Now that same question, I suppose, could have been done another way. If we were to condense these logs together, we could have raised this 3rd power up, we could have raised this 5th power up, and then we could have added the logs together by multiplying their inside things using that product rule. Frankly, I don't think that would have been easier, because that would have given me some really large numbers, and if I'm not using a calculator, I don't really enjoy working with large numbers, so I think the way we did it the first time was the best. So here, a natural log of all of this hot mess is going to be expanded, which means we're not going to stop until we have multiple logarithms, there's no more exponents, and inside each logarithm there's just one thing. So the first thing they did was they separated it into a subtraction problem where it was the log of the numerator minus the log of the denominator, and then within each of those logs, maybe you notice that there's a multiplication problem. So they split the multiplication problem up into log of 8 plus log of x to the 5th, and then they did something similar here, except this one we had to be extra careful because there was already a subtraction sign. So when you split this into log 3 plus log y squared, but remembered that we're subtracting all of it, they went ahead and they distributed. The other thing you could have done was put the subtraction sign and then rewritten the logs as the addition problem like you were intending to do. eventually you have to distribute the subtraction sign, so they're going to end up this in a minute. And then finally, we're totally expanded only when all the exponents come down in front of their logarithms. So they rewrote this exponent and this exponent down in front of their logarithm. Whoop, got a little crazy there. And then this is their final answer for the complete expansion of that logarithm. So, expanding logs is, I think, a little trickier than condensing, because when you're condensing, it's really obvious when you're done because you get down to one logarithm. When you're expanding, you just have to break it apart into as many logs as you need. So sometimes I'll ask my algebra students, like, okay, before we start the problem, how many logs are we going to have at the end of this question? And we kind of count up how many bases we have going on. All right, so let's try this without a calculator. So ignore the 2 for a second. Log base 3 of 27. If we could rewrite 27 as base 3, we'll be good to go. That's 3 to the 3rd power. Well, log base 3 of 3 cancels, and you get 2 times 3. Okay, same thing here. Ignore the 4 for a second. If I could rewrite 1/3 as a 3, I would rewrite it as 3 to the negative 1st power. So log base 3 of 3 cancels, and you have 4 times negative 1. And then this is 6, and this is plus negative 4, so my answer is 2. That problem, I think I probably could have done pretty nicely if I would have condensed it, but you know, to be honest, I don't like when the logs are condensed and evaluating without a calculator. I just don't. The logarithm of a sum or difference does not equal the sum and difference of the logarithms themselves. So if within a logarithm you have an addition problem or a subtraction problem, it's not okay to separate them into 2 different logarithms that way. That's not the same thing. That's not how the property works. And that was kind of comparable to an exponent property that kids used to confuse, so keep that in mind. All right, so we are just expanding. And if I look inside this logarithm, which is base 3, I have 5r and then t. So I have 3 bases, meaning I'm going to end up with 3 logarithms when I'm all done. So I'm going to start by splitting up the division into log of the numerator minus log of the denominator. And then the other thing I'm going to do, because I don't like this cube root of t squared, I'm going to rewrite that as an exponent. I'm going to rewrite it as t to the 2/3 power. Because that's going to be one of my exponent logarithm properties. So when I expand this logarithm, it's a multiplication problem at the moment. Oops, I lost my base. All right, log base 3 of 5 plus log base 3 of r to the 5th, and I still have minus log base 3 of t to the 2/3. And then the final step for me is always to look at my exponents and then bring them down in front. So here we go. This becomes log base 3 of 5 still, plus 5 log base 3 of r, minus 2/3 log base 3 of t. Fully expanded because every log just has one thing inside of it. If you want to keep using parentheses around what's inside your logarithm, you go right ahead. It surely doesn't hurt. In fact, I think it might be nice to see those parentheses once in a while. Alright, let's take a look at this next question. So we have a minus 2 is one of the bases, b plus 4 is another base. It's being raised to the 6th power, and then we have b to the 5th in the denominator. So I'm going to start by expanding the numerator minus the denominator. Got a lot of parentheses going on here, huh? And some of you got so good at this in Algebra 2 that you could actually expand all the way down to the final answer without doing much work at all, and that's awesome. Inside this logarithm, I still have a multiplication problem, so we're going to split that up. So I have log of a minus 2 plus log of b plus 4 to the 6th power still, and that's the only thing being raised to the 6th power, minus log base b to the 5th power, and then finally any exponents can come down in front. So that exponent comes down and that exponent comes down. So log of a minus 2, which you cannot split, plus 6 log of b plus 4, which you cannot split, minus 5 log b. Alright, so I told you we're just going to, the same properties, we're just stepping it up quite a bit from our Algebra 2 lives. So condensing. I like condensing a lot better because it's easier for me to do. I know when I'm done because it's just one logarithm. So whenever I'm doing these, like a bunch of them on a worksheet or for homework, somewhere where I'm going to put my answer, I'm just going to write like log base 9 and then a big empty parenthesis, like waiting for all of my answers to be placed there. So we're going to do all those steps in reverse. So the 11th power and the 5th power are going to come back up into their exponent position. So here we have log base 9 of x minus 3 to the 11th power, yuck, minus log base 9, and I'm going to go ahead and use parentheses around the 2x. So it's raised to the 5th power, quantity raised to the 5th power. So now when we condense a subtraction problem back together, it becomes a quotient. So I think I'm ready to give my answer. The numerator is x minus 3 to the 11th power, and the denominator is 2x to the 5th power. Now within the parentheses set, sometimes you have to watch out for like further simplification. This doesn't have any, so just be done. Alright, similarly here, exponents are going to go back up, and this exponent's going to go back up. So we have natural log of quantity 2h plus k to the 3/4 power. That's lovely. And then plus natural log of 2h plus k to the 1/4 power. And then condensing that back down into one logarithm. Oh, you know, I didn't notice at the beginning, but the 2h plus k, those are like terms, if you will. So, whoopsies on my part. So 2h plus k to the 3/4 times 2h plus k to the 1/4. Since those are the same base, I really could have used my exponent properties now and added those together and got 2h plus k to the 1st power. So, whoops on my part. This was natural log of 2h plus k. You can say to the 1st power, or you can just say 2h plus k within that logarithm. In hindsight, I could have just added these like terms together. 3/4 of this term plus 1/4 of that term is 1 of that term. So, my bad. I didn't notice. Alright, so here's just some more examples of condensing and expanding. Well, these are expanding. So, I'm going to kind of look ahead if you don't mind and make sure I don't have anything crazy coming up. Alright. So, guided practice questions. Remember, these are not on your notes anywhere. For the sake of time, I'm going to skip over these guided practice ones because I don't have a ton of time left. I've got a class coming in 15 minutes, so moving on. Change a base formula. Your calculator has a lot of cool features on it, and it has a natural and common logarithm button on the main keypad, and all of your logarithms can be rewritten in terms of either a natural log or a common log if you use what's called the change a base formula. So it works because if you think about how we solve logarithmic equations or exponential equations, we apply logarithms to both sides, and then we can rewrite them in terms of a ratio because we're going to do a bunch of algebra to figure out, you know, what the variable is or what the unknown is. So I think it says why this works here. So later on, when we start solving exponential equations, I'm going to come back to this idea and show you why change of base works exactly. So here's the idea. If you have a logarithm of a unfriendly base, so not a common log, base 10, or a natural log, which is base e, then you can rewrite it as a common or natural log of whatever this number is divided by common or natural log of whatever the base is. So you just have to make sure you're using the same button each time. So either common log over common log or natural log over natural log. So let's take a look at this question here. It's already kind of done for you. But log base 2 of 7, that's not a nice, pretty answer. But we could rewrite this in our calculator by doing the natural log of 7 divided by the natural log of 2. Just make sure when you're typing that you close off the natural logarithms, and it is going to be an approximation when it's not a nice answer. I would never have you do these like uncommon base ones without a calculator, because I'd have to give you a chart, and no one wants to use a chart. So here, and this works for common log or natural log. In this particular question, whoever did this decided to switch to a common log, excuse me. So they did natural log, common log of 10 divided by common log of 1/3, and they got that funky little answer. So here, if we're practicing these, we could type in, and I always use, this sounds awful, natural log because it's 2 letters instead of 3, and it's easier for me to write. So 631 divided by the natural log of 32, and it gets roughly 1.8603. So then here, you know, again, natural log for me all the way. So natural log of 47 divided by natural log of 11. And then when I type that in, I get roughly 1.6056. So the math behind it makes a lot of sense once we talk about actually solving exponential and logarithmic equations. So here's some more practice examples. If we're in class, I'm going to do as many of these as we need. If we got to save them for warm-ups, that's okay. But I'm going to go ahead and skip over these for now. But go ahead and jot these down. Freeze the video and jot these down if you need some more practice. That one's crossed off, so we're not going to do that. All right. Oh, you know what? I lied. That's totally in your notes. Okay. So let's do one. Let's see. I'm going to do this one because I just wrote your test and there is one that's kind of like that on it. So let's expand this logarithm, this natural logarithm, first into the subtraction of the numerator minus the denominator. And then instead of 3x plus 2 square rooted, I'm going to rewrite that as 3x plus 2 to the 1/2 power. So then there's nothing inside the logarithm as far as multiplication problems anymore, but these exponents do need to come down. Whoopsies. Having some tech difficulties. It must be Friday. All right, there we go. So we have 2 times the natural log of x minus 1/2 times the natural log of 3x plus 2. And remember, you cannot break up an addition problem inside of a logarithm. Nothing happens with that. All right, apparently Mrs. Hoffbar did not like number 11, so she went ahead and crossed it off. I didn't think it was too bad. It's all right. Okay. Here's some more practice with condensing. I would really, really, really like to look at number 15 because there's one that's kind of sneaky like this on your test. So putting exponents back up is something we're going to start with. So this exponent goes back up. The other thing I noticed about number 15 is the subtraction is for everything right here, which means that all of this is going to be in the denominator of my fraction. So when I condense these logs together, these are going to be in my numerator. So I have log base 3 of xy. But in my denominator, I end up with x times z to the 3rd. But this would not be a good answer because within the logarithm, you should notice that the x's are going to cancel out. And if I look back algebraically, if I would have looked a little more carefully, right here I should have noticed that these log base 3 of x's end up canceling out because of the subtraction. So it doesn't really matter when you simplify, whether it's before you start condensing or after, you just need to remember to simplify. So final answer here, log base 3 of y over z to the 3rd power. All right, there we go. Moving along. Richter scale, great application of our logarithm. So R is the magnitude and I measures the intensity of the wave, and the initial intensity being 1. So this is the ratio formula for the Richter scale. Pretty boring since this is always going to be a 1, comparing it to like no intensity, or a unit of 1 intensity. So in Guam in 2008, they had an earthquake that measured 6.7 on the Richter scale. So if I set that up, I get 6.7 in for R equals log base 10 of some intensity over 1. So instead of saying over 1, I'm just going to say of some intensity. If I think about, like, there's a few different ways we can solve this. We can do the rewriting formula that we learned from the previous unit, which is really just what's called exponentiation. To undo a logarithm of base 10, what you're really doing is you're exponentiating with a 10. So you're like shoving a base 10 underneath the whole problem. So you end up with 10 to the 6.7 power equals 10 to the log base 10 of I. So that rewriting formula that we learned in the previous section, this is where it comes from. The 10 to the log base 10 cancel, and you just get I equals 10 to the 6.7 power. So when we say like base to the answer equals the number, this is what we're talking about. So on my calculator, 10 to the 6.7 power is like 5,011,872-ish. It's got some decimal points after it. And I don't really know what they're measuring this in. It's intensity of wave energy, so I'm sure it has a label, but you know, pretty stinking intense is the answer to that one. We're going to have a whole section on how to solve exponential and logarithmic equations, and we're going to concentrate a lot on why it works, what are we doing to isolate the variables, and we're going to really concentrate and understand where all these little logarithm tricks and formulas are coming from. So you do have a book assignment, probably has been shortened, so make sure you look for that. Our main goal right now is to get ready for our no calculator logarithm and exponentials test, and then eventually we'll work on the things that do require calculators.